So let's take another question now. Now what I want you to do is I want you to count the number of leaves. How many leaves do you say in this tree? Leaf means nodes that do not have any children. There are 3 leaves in this tree. So can somebody come up with a similar sort of equation that we had written earlier for the count of leaves as well? What do you have to do? You have to break your entire big tree into a root and a left subtree and a right subtree. Okay, tell me one thing. The previous equation that we had written, that equation was count of leaves in the tree rooted at R is 1 plus count of leaves in R left plus count of nodes, not leaves, in R right. Will this equation hold true if I have to count the number of leaves also? Will it make sense? The answer is no, it will not make sense, because fundamentally here you are saying that, hey, the number of leaves in this is equals to 1 plus the number of leaves in this plus the number of leaves in that. No, wrong. Why you are counting 1 for this? This is not a leaf. If it has some children with it, how can it be a leaf? So this equation is not right. But if you omit this 1 from here, will now this equation be right to count the number of leaves? The answer is yes, because now you can say that the number of leaves in this entire tree can be thought of as number of leaves in left subtree plus the number of leaves in right subtree. As simple as that. Is that now making sense to all? So now if I have to code it, let's go ahead. So let's say int count. It takes the node. Okay, so I'll keep everything the same. I'll say if root is null. So if root is null, that means you are talking about a subtree which is empty. An empty tree has no nodes, so it has no leaves. So here I'll return 0. And otherwise, for the normal nodes, I'll return the count of leaves in its left subtree, and I'll add to it the count of nodes in the right subtree. Is this code correct according to you? Yes or no? This code is not correct. Just think of it. What will it return when I run this piece of code on this input? See, I have already run another piece of code on this input. I want you guys to run now this new piece of code on this input. See what you get. Most of you are saying you will get 0. You will always get 0. Is that true? Okay, let's do some work. The way I have created this kind of diagram for the previous code, please create a new sort of diagram on the current code. Okay, see what will happen. Let's keep watching, everyone. I'll erase these things. Okay, see, the flow will be same. From count of 2, you will come to count of 3. From count of 3 to count of 5. From count of 5, you will call count of null. And at null, you are returning 0. You return 0. You return 0. Now, for the normal cases, you are just adding what you get from left and right. From left and right, you got 0. 0 plus 0 will be 0. That you will return. Similarly, from here, you will return 0 plus 0. And again, from here, you will return 0 plus 0. Similarly, from here also, you will just return 0, 0. You are just returning 0 plus 0 plus 0. So eventually, you will only return 0. If this is the code that you write. Is that making sense to everyone? That why you will only be returning 0 in this case? So this is very important to understand. So what to fix? What is the very, very fundamental mistake that we are doing over here? The very fundamental mistake that we are doing over here is we are never counting the leaves. We are just returning 0. We are never counting the leaves. This thing is fundamentally correct, but this has a base case. It has a base case for what? It has a base case for the nodes that are actually the leaves. Because when you touch upon a node which is actually a leaf, so I would say if R is a leaf, then you should return 1. Why you should return 1? Because yeah, it is a leaf. So if you are talking about the subtree rooted over here, there is only 1 node in it. So you should just return 1 from here, symbolizing that. Does it make sense to all? Yes or no? You know, these are the kind of cases that you have to handle. I told you at the beginning when you write the code, you will have to handle some special scenarios, and most of the time they'll be happening for leaves or for the roots. Okay, now can you check whether a node is a leaf or not? It is very easy to check. So if this is R, you just have to check if R left is null, and if R right is also null, then I can say it is a leaf, and then I can return 1 in that scenario. So let me change it. I would say if R left is null and R right is also null, that means R is a leaf, and in the subtree rooted at leaf, there is only one leaf. So I'll return 1 from here. Now, is this code correct? It looks like it is correct, but it can still mess up with me. When will it mess up with me? Think about that. So let's take a look. Let's say you are at count of 4. At count of 4, you would make a call to count of null, correct? When you make a call to count of null, what you will do is here you will check for count, you will check for R arrow left. And because your R is null, you will end up getting a null pointer exception. So this code is not null safe. Not null safe means if the past value of R is null, this code can mess up. So you have to take additional handling of the case when your R becomes null. For that, you can add your first condition here. It will be same as the previous condition. If R is null, return 0. Theoretically, it is trying to say that if the subtree is empty, return 0, which is correct. So it will not lead to any wrong output, but what it does is it protects you from null pointer exception. So now this code is perfectly correct. If you make a call to null, you return 0 from here. And if you make a call to a node that is leaf, you return 1 from there. And now if you return the proper things, you will see it will work properly and it will be all right. So there are 2 termination conditions over here. First termination condition is when you touch a null, and second termination condition is when you actually touch a node that is a leaf. Is it making sense, all the different nuances which we encountered while writing this code? Yes, no? Cool. Now let's talk about the time complexity of this code. This code and also the last code that was counting the number of nodes. It'll be order of n. Good. Why it'll be order of n? Because whenever you have a recursive code, you just have to see that how many times this code is touching a node. Now here I can clearly see we are touching a node only once. And whenever we are touching a node, we are doing very trivial number of operations. We are just adding 2 integers that have been returned to us. So adding 2 integers is constant time operation. So I can say at every node, I am doing constant time operation, which is order 1 operation. Now, because there are n nodes, so n into order 1 can be written as order n. So this code and the last code, that was doing 2 additions. It was doing 1 plus count of left plus count of right. There was also 2 additions is also constant time, order 1 you can write it. So I can say the time complexity is going to be order of n. Is it making sense to each one here? Yes, no? And how about the space complexity? So let me see how much you have understood recursion. Is there some extra space we are using in this particular code? Yes or no? First answer that. Recursive stack. Yes or no? Recursion internally creates a recursive stack. For example, when you are at count of 2, you call count of 3, you call count of 5. So what happens is this entire thing that you have goes in a recursive stack. So this function has on its top this function, and this function has on its top this function. So it means that if, let's say, this tree had a height of this much, then the largest recursive stack that would have got created would have been of this much. And what is this? This kind of thing is also called as height of the tree. This is height of the tree, how longer the tree is or how high the tree is. So I can say that, hey, the space complexity is definitely there because recursion internally maintains a recursive stack, and the height of that recursive stack will depend upon the height of the tree. So your extra space is going to be order of h. What can be the maximum value of h? If there are n nodes in the tree, what can be the maximum value of h? So I just told you it can be n if the tree is completely skewed. Imagine all the nodes lying like that. It will be a skewed tree. In that case, your extra space would also be order of n. Yeah.